Alright guys, video number 3, introducing complex numbers as vectors and polar coordinates. So now we're going to get to the polar part. So the polar part has to do with the fact that we now are going to have a new coordinate system. Previously we always dealt with x and y. What we're going to do here is we're going to say, you know what, points can be identified in another way. I can identify a point based off of how far it is from the origin and knowing what angle it's directed at. Okay, so for example, this one right here, I've got point P there. If I know how far this is, if I know the radius of my circle, and I know the angle at which it's located, I can find this exact point because I go to that angle, that direction, and then I go that specific distance, and I have a location. And so all points can be identified using polar coordinates, in which we have r, comma, theta. All right, now you can go into 3 dimensions by adding another angle in there, but we're not going to worry about that for now. What I do want us to recognize is that we can actually relate this back to our Cartesian coordinates, right? Because we know that P in Cartesian coordinates, if this was x and y, would be r cosine theta, right? Because cosine is the x, and then for the y value, the opposite side, we got r sine theta. Okay, so we can make this relationship between the polar and the Cartesian in that way, where x is r cosine theta, y is r sine theta, which essentially means that we could write this vector z in terms of r cosine theta. So if we know what its location is in polar coordinates, we can do r cosine theta plus I r sine theta, right? Because now we're looking at this, the x as being the real, and we're looking at the y as being the imaginary. And so the cosine theta is positive, and then we're going to add on the imaginary piece right there. Now with this, generally what we'll do is we'll say, okay, well, z equals, and we'll factor out the r, so we have cosine theta plus I sine theta, because you're going to get this same thing every time. And so this whole cosine theta, I sine theta, we'll usually just write as z equals r cis theta. So we have a new trigonometric function, more or less, that deals with polar coordinates and the imaginary, the complex numbers. Now it's cis because of the cosine, I for imaginary, and sine right there. So that's your r cis theta. And so r cis theta is cosine theta plus I sine theta. So the other thing to recognize, of course, is that r is just the length of z, or modulus of z. Okay? So essentially we can say that z equals modulus of z times cis of theta. Okay, so hopefully these things you'll see will be comfortable for you and helpful for you as you go forth with some of the other questions. All right, so let's look at, let's say, okay, z equals the length of z, the modulus of z times cis theta. Well, what would that make the conjugate of z? Okay. Well, remember the conjugate of z, when we looked at it on the Argand diagram, the conjugate of z just ended up down here, right? Because that meant that the real part was staying the same and the imaginary part was then going the opposite direction. And so therefore, the r is going to be exactly the same, so we can write that still as the same modulus. What's going to change is the fact that now we're going to have the negative angle of before. So it's just cis of negative theta. And that's a property that will be helpful to you as you're working through various problems. Okay, so let's do a couple other things. Let's take something in this polar form. Let's say we've got z equals 2 cis 5 pi over 6. And we want to write that in Cartesian form. Okay, so let's see what we can do with that. All right, so the first thing that we're going to do is we're going to break up this cis. So I'm going to rewrite it as z equals 2 times, and then the cis is going to be cosine of 5 pi over 6 plus I times sine of 5 pi over 6. All right, and then we'll go ahead and put that into this, and so we'll go z equals, we can find cosine of 5 pi over 6, right? So if we just go, make our 5 pi over 6 here, it's not quite, 1, 2, 3, 4, 5, 5 would be over here, which makes this a 30. So we've got 1, 2, root 3. And so cosine would be the adjacent, which would be negative root 3 over 2. So I got 2 times negative root 3 over 2 plus, and then our imaginary part, the sine of 5 pi over 6 would be the opposite, so 1 over root 3, so plus 1 over, and that's again negative root 3, opposite over hypotenuse. Man, I'm just crazy today. And that's with our I. And so we can put all that together and we get z equals negative root 3 plus 2 times that, which would give you plus I. And so there, now you have it in the Cartesian form, where you could just go to negative 3 in the imaginary, or in the real direction, and then up 1 in the imaginary direction. So real, negative root 3, imaginary, 1. Okay, let's look at maybe one other problem here, and then I'll give you one last thing. So let's start with z equals 1 minus I, and we want to do that in polar coordinates. Okay, so the first thing that we need to do, well, we need to do a couple of things. We need to find an angle, and we need to find r. So r is easy enough because r is just the modulus of z. So we've got 1 and 1, so that'll be the square root of 1 squared plus 1 squared, which will be the square root of 2. So that's fine. And then what we'll do is we'll say, okay, now we need to find an angle. So if we think about this in terms of the angle, so to get this, we just go 1 in the real direction. So let's just say that's 1 right there. And then we go negative 1 in the I direction. And so then we've got this vector right here. Oops, which we know the length already. Oh, come on. Yikes. There we go. So we already have the length. And we also know the angle, because if it's the same on each side, then it's 45. So it's a 45-degree angle. So with that, we can now create our angle and our vector in polar form. So we can just go z equals the length, which is root 2, cis, and then the angle, which is negative 45, or negative pi over 4. So there you go. We just created this angle, this vector, which was in Cartesian coordinates, and we did it in polar. Now, the other thing that I want to mention is that you can actually also do a vector in the Euler setup, which is r e to the I theta. Now, we won't do a whole lot with this, but you will note that sometimes it'll be helpful, and you'll see some examples in the book and some different things where it'll be useful, but we're not going to go into it too much right now. But just know that this is also an okay format for the polar coordinates, with r and then I to the theta as the exponent of the. And like I say, in the textbook you'll see some examples of when that could be useful. Alright, and that's it for this video.